Ladies and gentlemen, welcome to the Geological Society of London and to this, the fourth Society London lecture in 2015 entitled Earth's Climate Evolution. My name is Ted Neild and I am the editor of Geoscientist. Free copies available outside in the Law Library. And it is my pleasure today to introduce our speaker, Dr. Colin Summerhayes of the Scott Polar Research Institute at the University of Cambridge. And I've been asked also, you have all received a questionnaire for customer feedback. You don't have to put your name on it and there's no prize, but I'm afraid. But if you could hand it in when you leave, the organizers would be very grateful. We've come a long way from the notion that erratic blocks of rock on British hills were deposited there by Noah's flood. The past 20 years have seen a dramatic increase in our knowledge of the variability of past climates and its causes, which underpins our understanding of what our climate is doing now and what it may do in the future. These advances deserve to be more widely known. They show that our climate operates within narrow natural envelopes. We should still be in the little ice age envelope, but our emissions have moved our climate into new uncharted territory. Man has become a geological agent. Our speaker, Dr. Colin Summerhayes, is a marine geochemist with expertise in determining past climates from the characteristics of marine sediments. He's an emeritus associate undertaking research on climate history at the Scott Polar Research Institute in Cambridge. Formerly, he was executive director of the Scientific Committee on Antarctic Research, director of the Global Ocean Observing System for UNESCO's Intergovernmental Oceanographic Commission, director of the UK Institute of Oceanographic Sciences Deakin Laboratory, and deputy director of the National Oceanography Centre. Colin has worked in academia, government, and industry. His many books include Earth's Climate Evolution, Antarctic Climate Change and the Environment, Oceans 2020, Science Trends and the Challenge of Sustainability, Oceanography, an Illustrated Guide, Upwelling in the Ocean, Upwelling Systems, and North Atlantic Paleoceanography. He has also served as Vice President of the Geological Society of London and is past President of the Society for Underwater Technology. Ladies and gentlemen, please welcome Dr. Colin Summerhayes.
Thank you, everybody. It's a great pleasure to be here to talk to you today about my favorite subject, which is Earth's climate evolution. The climate is always changing. You hear this often, don't you? You hear it down the pub, maybe, at the golf club, all sorts of places. Geologists are very fond of telling you this. The problem is that really it is a mindless mantra, unless you take the trouble to engage your brain and figure out why the climate changed in particular ways when it did. Otherwise, the phrase, the climate is always changing, means nothing. So we're going to look at Earth's climate evolution from the perspective of what rocks and ice have to tell us about climate change, and it is quite a lot. I start by just reminding all of us here that the words of James Hutton are rather important. In 1795, he published his theory of the Earth. This was where the idea first came about that the present is the key to the past. But what a lot of people don't know or have long forgotten is that he also said that the past was the key to the future. That is, if the conditions that gave rise to particular kinds of sediments in the past were repeated at some time in the future, then you would expect the same result. So what he was thinking of was geology as a predictive agent. Some of you will know that recently the Council of the Society decided that it actually needed on its website and for its fellows a statement on climate change from the geological perspective. And you can find this statement on the website. The web address is there. And I was asked to chair the drafting group that wrote this. You can see the names of my colleagues who helped to write this statement. And our first statement appeared on the website and also in the Geoscientist in November 2010. But we went on to write an addendum to this climate change statement in 2013 to take account of the evolving literature on this topic. And one of the conclusions to this, this study of ours is right here, that in the light of the evidence presented here, it's reasonable to conclude that emitting further large amounts of CO2 into the atmosphere over time is likely to be unwise, uncomfortable though that thought might be. So that's the context in which I'm going to be talking to you this afternoon. And I start by going back to our forebears in the 19th century, people like Charles Lyell, who was twice a president of the society, who wrote the Principles of Geology in 1830 to 1833, which is well worth reading if you ever get the chance to do that, recently reissued by Penguin. And these people at that time they knew a lot of the same sorts of changes were taking place that we have been working on in recent years. They just had far fewer data than we do. And they had far less sophisticated ways of analyzing that data. We're the beneficiaries of all sorts of geological developments in the almost 200 years since then. So the things that they were obsessed with are these: the great cooling from the Cretaceous to the present, the origins of the Ice Age. In fact, Lyell didn't even know that there was an Ice Age, not until 1837, when Louis Agassiz, a Swiss geologist, came along and said, aha, the reason for all these blocks being distributed over Western Europe isn't because of Noah's flood or anything like that. It's because there was a large ice sheet there, and when the ice sheet melted away, it left all this debris behind. That led to long years of argument between himself and Charles Lyell. In the end, Agassiz won, just for those who like to keep score. Then we have changes within individual continents or continental pieces, like the UK, for example. You can see in the UK's rocks how the climate has changed with time. Lyell was well aware of these changes, and he dreamed up ways in which he could try to explain that, and I'll show one of those to you in a moment. Also, at Lyell's time, the astronomers were well aware that the Earth's orbit had changed its shape over time in a regular way, and this must have affected our climate. Lyell and his colleagues, unfortunately, were able at the time to see how those changes were reflected in the geology, and that was partly because they couldn't date rocks very well. So we'll talk about evolution in that area too. And then there was the role of the greenhouse gases. We talk a lot these days about greenhouse gases like carbon dioxide. But the greenhouse gases were not discovered until 1859, well after Lyell had written his principles. And it took a long while before people cottoned on to actually how they work. Not until about the 1950s, in fact, almost 100 years after they were discovered, did we really understand how it was that they worked. And then finally, I'm going to deal with the role of sunspots. Even at the beginning of the 1800s, savants, you might call them, rather than geologists, understood that there were changes in the wheat harvest, and those changes correlated with changes in the sunspot cycle, the 11-year sunspot cycle. So let's go on then to see what Lyell was talking about when he was talking about the great cooling. The thing here is that he realized, because of his studies of mollusks, he actually did a lot of studies of mollusks all across Western Europe, and he realized from these that there had to have been a significant cooling over the past 50 to 60 millions of years. And when he was getting ready to write his principles, he stumbled across the work of the great German polymath Alexander von Humboldt. And what Humboldt had done was he'd gone around the world collecting temperature data from cities from different times of year. And he then realized that he could join up different cities with the same temperature at the same time of year with lines, which he called isothermal lines. And when you took any given season, those isothermal lines were much like the lines of latitude, as you might expect, you know, cold temperatures near the poles, hot temperatures near the equator, and so on. So these were rather like climate zones, what we would understand as climate zones. And Lyell thought this was a rather attractive idea, and he thought, I've got a way here of explaining how the climate changes I can see in British geology could be caused by the continent of Western Europe, including the UK, migrating across these climate zones. And he was so excited about this, he wrote to his paleontologist friend, Gideon Mantell. He said, I will give you a receipt, at that time that was a word for recipe, for growing tree ferns at the pole, or if it suits me, pines at the equator, walruses, which are Arctic animals, under the line, meaning the equator, and crocodiles in the Arctic Circle. And he went on in subsequent publications to say that continents, therefore, although permanent for whole geological epochs, shift their positions entirely in the course of ages. So this is the precursor to continental drift. He just didn't have the data to be able to see how the continents themselves might have moved. For that, we had to wait for this man here. This is Alfred Wegener. And Wegener came up with the concept of continental drift. And this is his reconstruction for the Carboniferous period 300 million years ago. That's when all the world's major coal deposits were laid down. So what you see here is he fitted South America into Africa. He has Antarctica down here, Australia and India all linked together. And up here, North America joined to Europe and to Asia. Now, he found great difficulty in getting this idea accepted. And that was partly because of the idea of Viennese geologist Eduard Suess. And Suess had realized, just as Wegener did, that when you took the southern continents and looked at their animals and their flora, there were lots of linkages. And what he had supposed, Suess had supposed, was that the continents had been permanently in their present positions, but they had been joined by things he called land bridges. And these plants and these animals had migrated across these land bridges, and that's why you found very similar plants and animals on all these continental fragments. Well, we know now that that was a silly idea because there is no way that the basaltic floors of the ocean basins kind of absorbed large pieces. When I was an undergraduate, before plate tectonics, mind you, I remember having to write essays like continental drift versus land bridges, discuss. Lots of arm waving, lots of arm waving. So this was part of the reason why he had difficulty getting his ideas accepted. But he came across this man here. This bearded gentleman here is Vladimir Köppen, a German born in Russia who later became a very prominent meteorologist and climatologist in Germany. And because Köppen was a climatologist, he saw Wegener's maps and he was really taken with these because it gave him a means of taking climatology back into the past. And the two of them ganged up and they wrote in 1924 a book with a German title, which basically means the climates of the geological past, which was never translated into English. It is now being translated into English and it should be published actually this year. And I think you'll find it a very interesting read. Anyway, so what they did was they said, okay, we've got desert deposits, Aeolian sands, we've got ice indicators, we've got salts, which are evaporitic and must have formed in arid environments, and we've got plant indicators, and we've got coal, which suggests humid climates, and we can put all this on these maps. And so they did. So here is that Carboniferous map, and on it you see, you probably can't see from further back than the back row, There are little E's here. E is the abbreviation for the German for ice. So that closed the gateway into the Pacific. There was the gateway from across Indonesia was squeezed by New Guinea and Australia still moving north, but there still was a gap there. And the gap through here had closed because Africa was now impinging on Europe and pushing up the beginnings of the Alps. So what you had was a new circulation which came round Cape Town, up towards Florida, and then off into the polar regions, much like our circulation does today. And there was similarly a southern current, like the Brazil current today, which took heat down towards the polar regions. So what we had at this time was a lot of polar heating because of these massive changes induced not by extra heat coming to the globe from something in the sun, but simply by the changes on the face of the Earth caused by plate tectonics. Now, one of the things that I mentioned that Lyle was interested in was this whole subject of the changes in the Earth's orbit. Now, this is a little bit complicated, so I'm going to walk you through this. We have three things to think about. I call this the climate clock. What we're dealing with basically is how celestial mechanics affect climate. And the main reason is there's the Earth's orbit sweeping around, and it's affected by the pull of the giant gas planets, Jupiter and Venus. And they distort the Earth's orbital pattern in a regular way, like clockwork. And so we have three things to look at. One is the eccentricity. So let's look at that first. The Earth's orbit is nearly circular, but the sun is not central. That's why we call it eccentric. So right now, the Earth is here in winter, and so it's fairly close to the sun. So our winters are, relatively speaking, warm, but the summer is over here, further from the sun, so our summers are, relatively speaking, cool. Now, the orbit will change from circular to this much more elliptical path over a 100,000-year period. And so what we see when we plot the eccentricity from 1 million years ago to the present is we see this 100,000-year cycle. We can also see that it's superimposed on these broad humps. This is a 400,000-year cycle. So these are the cycles induced by these patterns induced by the way the planets interact. And what we know about that is that the seasons are shorter and warmer at points close to the sun. So the winter season is relatively short, and the summer season over here is rather longer. And the winter is relatively warmer because it's closer to the sun. When we have maximum eccentricity, that would be this big long ellipse, then the difference in the heat out here at what's called aphelion is 23% less than we would expect it to be when the Earth is closer to the sun. So it makes a big difference to our climate. Right now, this is up is cold and down is warm. So we are here in a relatively warm period. Now we need to think about the tilt of the Earth's axis. The tilt of the Earth's axis, you see depicted there, it changes from 21.5 to 24.5 degrees. Right now, it's 23, so our seasonality is kind of medium. And it will change from low seasonality to high seasonality. This is very effective at high latitudes in the polar regions. And we see that changing regularly, as you see with this high frequency, every 41,000 years. Now we move to the final one, which is the precession, and there we combine two signals. The first of these is what we call the axial precession, and that changes where the axis points at a given time. So right now, our axis, as you know from looking at the night sky, is pointed towards the pole star. Okay, but 11,000 years ago, it was pointed towards Vega, and it rotates around the axis, rather like a spinning top. You know, when you spin a top, it doesn't stay spinning like that. The top rotates in its own circle, and that's what is happening here. So that causes changes with a period of about 20,000 years or so. And the second one, equinoxes and solstices, migrates around the orbit. So right now, as we saw, in winter, the Earth is here. In summer, it's over there. But gradually, over 11,000 years, the Earth will rotate round so that summer now becomes over here, and the summers will then be significantly warmer. And then over the next 11,000 years, the summer will migrate back to where it is now. So that's another 20,000 year cycle. You combine those two, and what you get is this very high frequency wiggling that you see here. And just as these 100,000 year cycles are sited on top of a 400,000 year cycle, you can see from these sort of blobby characteristics here that this 20,000 year cyclicity is superimposed on the eccentricity cycles. You see those are the same blobs that you see up there. So Earth is now closest to the sun in midwinter, and in 11,000 years it will be closest in midsummer. So this also introduces regular changes into our climate system. Now back in the 1800s, we're going back to the 1800s, and one of the guys really interested in this was this fellow here, James Kroll, a Scotsman, who was trained himself in physics and was very interested in this whole subject of astronomy and its relation to climate. So what he did on this graph here, this is from one of his late 1800 publications, he said, right, there's today, in his case that meant 1800, and he said, I'm going to plot the eccentricity of the Earth's orbit for 3 million years beforehand and 1 million years afterwards. So all these little ticks that you can see at the bottom, they're spaced 50,000 years apart, right? So from 1800, that's 1 million years into the past. This is the next 1 million years into the past, and that's 3 million years into the past. And this is 1 million years into the future. Astronomers are very confident people. So where it's up, that's large eccentricity, so that would be cold. This, where we are in today, this is low eccentricity, so it's warm. He found great difficulty getting geologists to believe this, again, because they weren't very good at dividing geological time up. They knew that there were signs of glaciation that had repeated through time, but they really had no idea what the time gap was between those periods of glaciation, so they couldn't link up with what he was doing. For that, we had to wait until this fellow came along in 1920s. This is the Serbian, Milutin Milankovic, and he had much better access to astronomical calculations. He was an engineer, and he did similar calculations. Now, what he did was rather interesting. He took the eccentricity signal and the tilt of the x-axis signal and the precession signal and added them all together because he wanted to see how much incoming solar radiation we would get at a particular place on the Earth's surface. In this case, he was interested in 65 degrees north. Now, you imagine where that is, somewhere north of Oslo, up near the Arctic Circle. And if you had snow accumulating, and that snow stayed through the summer, and it kept staying through the summer, you'd have yourself a glaciation. But if it melted, you'd have yourself an interglacial. So that was why this was rather a critical latitude. So what he wanted to do then was calculate this incoming solar radiation, insolation for short, in June, the summer, at 65 degrees north. And this goes from today, on this side, well, actually, today for him, it was 1800, and back 600,000 years. So each of these ticks along the bottom, just as up here, these ticks are 50,000 years apart. And what you can see is he got very cold peaks going down. You can see them shaded. I'm sure you can see that from the back of the room. So this was a very interesting pattern. And he worked closely with Vladimir Koppen, our climatology fellow. And Koppen knew that German scientists working in the Alps had discovered that there was a whole series of glaciations that they called Gauss, Mindel, Riss, and Würm. And these glaciations came in these packages. And he thought, right, I've got 3 peaks here with Milankovic, and my German colleagues have got 3 peaks there. I've got 2 here, my German colleagues have got 2 there, another 2 here. In his mind, he saw that there was a link. Even though the geologists at the time couldn't accurately date those, he thought we must have a link. So this was the first sign that this theory was really working. So now we move to the modern era, and we're going to look at the work of this Belgian scientist. This is André Berger. And Berger, like us, had access to computers. So in the 1970s, he did his calculations. So there's eccentricity. Now we've got 1 million years ago on the right, and today on the left. So there's the eccentricity, 100,000 year cycles. There's the tilt of the axis, 41,000. And there's the precession, 20,000 or so. You combine them together in the computer, and you come up with the solar forcing, the insolation at 65 degrees north. And so there it is. Now, what he wanted to know was, did this link in with the geology of climate change? And to that, we turn to this man here. This is Nicholas Shackleton from Cambridge University, who was an expert in oxygen isotope analyses of fossils. And he worked closely with two Americans, Jim Hayes and John Embry. And this is their curve of 1 million years of climate history from deep ocean sediments. And what you see is cold, warm, cold, warm, cold, warm, and so on. All the gray bars here represent the warmest periods. And what you see is that this warm period correlates with that high solar forcing, this one with that high solar forcing, this one with that high solar, and so on. So for the first time, we had this fantastic, absolutely amazing, extraordinary linkage between the astronomical properties, the celestial mechanics, and what was happening to our climate. This was as big a breakthrough as plate tectonics. Now, we want to move away from sediment cores and see what the ice cores tell us, because ice cores are another way, like sediment cores, of recording the annual history of climate change. And here we're going to Antarctica. We're going to look at an ice core that's very long, but just to give you an example, here's a lad extruding an ice core from a shallow drilling apparatus, because he wants to look at the past few hundreds of years of climate history, and he'll cut pieces off, put them in a tray, cut pieces off, and send them off to the lab for analysis. But we're dealing with rather bigger scale than that. What we have is a drill rig that's going to drill to the bottom of the ice sheet, 3.5 kilometers down, and bring back a continuous ice core, which will show us all the climate changes in that period. So here it is, and at the bottom here is the scale. This goes down to 800,000 years ago, so almost 1 million years of climate history. And this is the temperature as deduced from isotopes. So you see today's temperatures, we're going to call those 0 for Antarctica, and the scale goes back to -9 degrees centigrade. Okay, so we go back through time, and 120,000 years ago, we have another warm period like today's, and here 200,000, and there 300,000, and there 400,000 years ago, we have these what we call interglacial, short warm periods. You see that most of the ice age here is cold. It's well under the blue line, which is today's temperature. But every now and then, you get these warm periods. And in these interglacials, these past 4, they were all warmer than today by 2 to 3 degrees centigrade. Now, what happens if you put ice on Antarctica? Where does the water come from? Out of the ocean. So what happens to sea level? It goes down. So let's look at sea level. This is the sea level curve. And we are looking at the turquoise curve. It goes down. There's the maximum lowering of temperature in the last glacial maximum to -9 degrees. And at that time, sea level, 20,000 years ago, was 130 meters lower than it is today. Isn't that amazing? See, you might have got your feet muddy. You could still have done it. So this tells us, if you follow that turquoise curve along, you see here and here and here, the turquoise curve comes above today's sea level. So what is this geological information telling us? It is saying, if you warm your climate by 2 to 3 degrees centigrade, your sea level will go up by 4 to 9 meters. There's a message for the future, folks. Now, I want to talk briefly about 2 things. First of all, how do we take measurements of temperature? And secondly, then, the history of carbon dioxide, because we're going to see how these 2 interact and interrelate. So first, let's deal with the temperature. And as I said to you, Shackleton was using isotopes, but it started with this man here. This is an Italian paleontologist, Cesare Emiliani, and he was very excited about what was happening in Harold Urey's group in Chicago in the 1950s. Urey was a famous Nobel chemist, and he'd realized that oxygen has 2 different isotopes. Now that means that the numbers of protons and neutrons, the numbers of neutrons were slightly different. One kind of oxygen had 16 and the other one had 18 protons and neutrons added together. Now he realized in a sort of eureka moment that what that meant was that if you evaporated water from the ocean, the H2 and O, that the lighter O with the 16 would go off with the water first, and your ocean would be left enriched in oxygen with 18. Okay, so there was a fractionation effect going on. And so if you then imagine that little animals in the water, the plankton, are eating that oxygen, then they will carry that signal to the seabed where you can capture it in cores of sediment. And so that's what he was doing. He started measuring oxygen isotopes down cores, and what he saw, there were lots of wiggles, many, many more wiggles from warm to cold than the geologists had found on land. We saw the geology findings earlier with Milankovitch. But he didn't really have long enough cores to take this back very far. So in 1968, the US and other countries began running a project called the Deep Sea Drilling Project, which is still running in one form or another today, using drill ships adapted from the oil industry, like the Joides Resolution here with a big derrick. And they can now drill down a few thousand kilometers into the deep sea floor and get very long cores of sediment going right back into Cretaceous and even Jurassic times, where they can look at these very tiny changes in isotopes. So here, the guy working on this recently is this fellow Jim Zakos from Santa Cruz. And what he's done here is he's used the oxygen isotopes, the ratio of 16 to 18, and plotted it against millions of years going back 10, 20, 30, 40, 50, 60, 70 million years. And there are the results. So you've got lots of oxygen 18 here. So that tells you the ocean water was very warm, and it declines with time, and not too steadily, but it declines with time to the present, where you have very cold ocean waters. And there are some kinks along the way. This big kink here is when the Antarctic ice sheet first formed, and then there was a sort of stable ice sheet for a while, and then a big drop here when the northern hemisphere ice sheets formed. So what we've seen here in these data is Lyell's Great Cooling, confirmed by an entirely different means. All very exciting stuff, and it can independently be confirmed by another means too. This young lady here is Jane Francis. She is the new director of the British Antarctic Survey in Cambridge, and Jane is a palynologist. She specializes in using fossil leaves and pollen and so on to understand past climate. So what she's done here, this is the same time scale going back, so there's 20 to 20, 40 to 40, 60 to 60 million years, but she's going back even further in Antarctica, and she's showing that the leaf data tell her that the temperatures in Antarctica declined steadily to from about 20 degrees to about 7 degrees by the time the first big ice sheet had formed. And 100 million years ago, this is her reconstruction of what Antarctica looked like at the time, painted by this artist, Bob Nichols. So very, very different from today's Antarctic. But what we have is independent confirmation by these two methods, plus Lyell's mollusks, that we had this big cooling. And it's interesting that we should have had that cooling, because the astronomers tell us that our star, like most stars, is growing in its output, and that the output of the sun has increased by 6% from 600 million years ago to the present. So we have to ask ourselves why this cooling has taken place. That then brings us to a discussion of the role of the greenhouse gases. Now, this fellow here, this is Joseph Fourier, a prominent French scientist who he's slightly conceitedly regarded himself as the Newton of heat. But he was a bright guy. He was a bright guy, give him his due, and he realized the air was warmer than it should be. And he thought that was because the sun was warming the surface of the Earth, some kind of radiation in the form of heat was coming off the Earth, and this was making the atmosphere warmer, but he didn't know how it was happening. We had to wait another 30 years until this wonderfully bearded Irishman came along, John Tyndall, and he used this, what I would call a Heath Robinson sort of apparatus. Here he had a heat source in this box, and into this tube he would put a gas. And then what he wanted to see, using this galvanometer over here, was how much heat was absorbed by that gas. You put oxygen in there, no deflection. You put nitrogen in there, no deflection. So it wasn't oxygen or nitrogen in the air that was causing the heat to be absorbed by the gases in his tube. Water vapor absorbed heat. Carbon dioxide, methane, and ozone, all of them absorbed heat in his tube, and then later, when he turned the heat source off, they re-emitted that heat. And so he felt, another eureka moment. I have discovered how the Earth's climate has changed or should change. And he went on to say, we're not allowed to write papers like this anymore. You know, it's flowery Victorian language here. That fluctuations in these gases could have produced all the mutations of climate which the researchers of geologists reveal. So now we have to try and understand how carbon dioxide works in the atmosphere. And there was a Swedish chap called Arrhenius tried to do this in the 1890s and came up with some interesting figures. But he didn't have enough information on what the spectrum of water vapor or carbon dioxide were in the atmosphere. For that, we had to wait until the 1950s and the Cold War. And at the time, of course, jet fighters were developed during the Second World War, right at the end of the Second World War, and they became quite prominent as we got into the 1950s. And the US Air Force wanted to figure out how they could shoot down Russian MiGs. Right? Those MiGs are putting out lots of heat. You've got a heat-seeking missile, great. But what's the effect of water vapor and carbon dioxide in the atmosphere going to be? You don't know because you can't measure the spectrum. So you have to measure it. So they poured lots of money into determining the spectrum of these gases in the atmosphere. They really helped to advance infrared spectroscopy as a major tool. So we know that the sun warms the Earth radiates to space via infrared radiation, and what we should see is the outgoing flux of radiation along this axis, and it's a wave number here. So at this peak, the red line shows you what the theoretically calculated infrared radiation should be at the top of the atmosphere. The black line shows you what it actually is. And the reason for this strange pattern is that these gases, these greenhouse gases, are absorbing infrared radiation and preventing it from going straight up. Here, there is no gas getting in the way, and so the black line and the red line are almost the same. The same there. So these two bits here are transparent windows where the radiation from the surface of the Earth goes straight out to space. Anywhere else, it's trapped temporarily by these gases, water vapor, nitrous oxide, carbon dioxide. Carbon dioxide carves that huge chunk out right there, ozone, methane, and more water vapor. So we can calculate, now that we understand this, that the carbon dioxide interrupts and reduces 20% of the outgoing radiation, and water vapor another 50%, and clouds also have a significant effect. So these are our greenhouse gases. So the question, now that we know that, the question then is, can we measure this stuff in geological materials? And the first person to realize that we could is, this is Hans Oeschger, who was running a team in Switzerland, and he had access to ice cores. Now, when you look carefully at the end of an ice core, I don't know whether you can see from the back of the room, but you can see these sort of little spots. Can you see those little spots there? Yes? Those are, they look like nodules. Those are bubbles of air trapped in the ice. And if you held that piece of ice to your ear, it would be going snap, crack, pop, like a breakfast cereal. That's the bubbles bursting. So in his lab, he was able to dissolve the ice and get the water, which gave him the oxygen isotopes for the temperature, and he was able to extract the air from the bubbles and measure the carbon dioxide concentration of the fossil air. So here is this is a proxy for the temperature, the isotope scale, and this is the carbon dioxide in the bubbles, and you see all the way down this 3.5 kilometer long dome sea core, you see a beautiful correlation between carbon dioxide and temperature. Very nice indeed. Now, some of you who've read the literature may have heard it said that the problem with carbon dioxide and temperature in ice cores is that the carbon dioxide lags the temperature. And that used to be thought until these French guys came along in 2013. This is Frédéric Parinin and his colleagues publishing in Science in 2013. And what they did was they took all the Antarctic ice cores they could find, dated from 22,000 years ago to about 11,000 years ago, 10,000 years ago, and they combined all those to get what they called the Antarctic temperature stack. So there you see the Antarctic temperatures flat, then a kink, a rise, a slight fall, and then another rise. And you'll see why I've circled those kinks in a moment. This is the stacked carbon dioxide content. Again, flat, rising, falling, rising. And these inflection points are exactly the same as the temperature. So the carbon dioxide and the temperature are changing at the same time. They are synchronous, not lagged. And there is a good reason for that. If you warm water, gases escape. If you cool water, it absorbs gases. And so you would expect, from the way in which the orbital changes warm the Southern Ocean, that when you warm the Southern Ocean, carbon dioxide is going to come out straight away. So let's look at our ice core again. Here's our temperatures going back 800,000 years along the scale at the bottom. And there's the carbon dioxide. And you read down, you see this warmth correlates with that high carbon dioxide. These two peaks are the same there. This peak is the same. This peak is the same. The carbon dioxide and temperature are moving together in these ice cores. And you can see also that the carbon dioxide is following a natural envelope between 180 and 280 parts per million. So what is the carbon dioxide doing as far as the temperature is concerned? What we know is carbon dioxide is a greenhouse gas. It should have an effect on the temperature. The orbital changes will also affect the temperature. So the orbital changes drive the temperature changes, and the temperature changes in the water around Antarctica lead to the carbon dioxide changes. And that carbon dioxide, when it gets into the air, reinforces the temperature change, probably to as much as 30 to 50%. It's a positive feedback. So the net result is that these large temperature rises are the products of two things: external driving from the forcing by the orbit, and internal feedbacks from the carbon dioxide in the Southern Ocean. So the question now is, where are we today? Well, we're up here, 400 parts per million. Now, what do you suppose would happen if you increase carbon dioxide by that amount? Answers on a postcard. I now want to talk briefly about the carbon cycle. I'm going to talk about the slow carbon cycle. Everybody in this room, I'm sure, is aware of the fast carbon cycle. All those lovely plants growing in your gardens right now, they are sucking carbon dioxide out of the atmosphere. When they die in the autumn and decompose, they're going to put the carbon dioxide back into the atmosphere in 1 year. That's the fast carbon cycle. This is the slow one. So here we have seafloor spreading, we have a mid-ocean ridge, and the volcanoes on the ridge are emitting carbon dioxide into the atmosphere. Okay, you with me there? That then mixes with water vapor to form a weak acid, carbonic acid, which falls with rain and dissolves calcium magnesium silicates in mountains. That process then carries the carbon dioxide from the atmosphere down through rivers into the ocean, and there it is used by plankton. The plankton use it in two ways. First of all, to build their soft parts with organic carbon, and secondly, to build their skeletons of calcium carbonate. Now, a large part of that material falls to the seabed and becomes carbonate sediment. Okay, so back to plate tectonics again. What happens with plate tectonics? On this side of the mid-ocean ridge, the seafloor is moving in this direction to the right, and it is meeting a continent over here, and it's diving down beneath the continent in the process known as subduction. And as the plate descends, it melts, and the carbon comes back up as carbon dioxide through island arc volcanoes. So these are the elements of the slow carbon cycle. And if you want to follow this up, this guy, Bob Berner, is the ace at this. He unfortunately just died. But you can read his book, 2004, The Phanerozoic Carbon Cycle, CO2 and Oxygen, published by Oxford University Press. I do recommend it to you. So can we now measure carbon dioxide back through time, beyond ice cores? No bubbles of air. How can we measure it? Well, there are several different ways of making these measurements. One is the little green box there. It says, you probably can't read that, it says stomata. If you look at the surface of a leaf, it's full of holes through which the plant breathes. If there's a lot of carbon dioxide in the atmosphere, it needs fewer holes. If there's little carbon dioxide in the atmosphere, it needs a lot of holes. So by looking at fossil leaves back through time and counting the stomata, we can come up with the stomatal index. And it tells us, along with these other other measurements that show the same thing. The word escapes me. But that from 65 million years ago, we saw a regular increase in carbon dioxide and then a regular decrease. And then since then, it's been more or less flat over here. So what's going on? That relates to the isotopic temperature graph that you saw earlier from Jim Zakos. Temperatures rise, the carbon dioxide goes up, and the temperatures rise, the carbon dioxide goes down, and the temperatures fall. What is happening here is another example of plate tectonics. You have to imagine that India now is moving north towards Asia, and in front of India is the floor of the Tethys Ocean, which has now disappeared, and it's covered in carbonate sediment. And as that ocean floor gets to Asia, it's subducted down under what is now Tibet, and the material melts as it goes down, and the carbon dioxide comes up in the island arcs around the Asian margin and gives us carbon dioxide in the atmosphere, which leads to warming. That's this part of the graph, okay? But then eventually, India itself crunches into Asia and jams up the subduction. No more subduction, no more carbon dioxide. Instead, what you have is the Himalaya beginning to rise. And so they become subject to chemical erosion, chemical weathering, which sucks carbon dioxide out of the atmosphere. So here you have a supply side activity, and there you have a sink. So you've got a source, and there is the sink, leading us back down to the typical values that we have today. So Berner has modeled all this. This is the black line is, the red line is Berner's model, back through time, a geochemical model. The pink shows you the error bars. So there's quite a lot of uncertainty about these figures. The black line shows you the data from this man, Dana Royer. That's those proxy values from actually measuring leaves and that sort of thing. So you see this pattern back through time. Very low values at the last big glaciation in the Carboniferous. Very low values today in the present glaciation. What was plate tectonics doing? Well, we can get a feel for that from the sea level curve. These are two different sea level curves. What they show is sea levels were higher here and here, presumably because there was more seafloor spreading, larger mid-ocean ridges displacing water onto the continent. And then here we have a time of continental collision when the continents come together, form Pangaea, Alfred Wegener's Pangaea, and so sea levels drop. And then similarly, we now have another sea level drop through here. So what we're looking at here is the times of CO2 source that relate to these actual measurements. And then here what we see is the weathering effects. When you slow seafloor spreading down, you expose the basalts on the seabed to weathering, and they form a carbon dioxide sink. So as you go down with sea level, you get more basalt weathering here and here. And then the other thing is, here we have mountains rising, the Andes, the Himalayas, and the Alps rising. Again, another carbon dioxide sink. But there's one further thing that's important. That is the role of plants. So here what we see is that this huge fall in carbon dioxide from about 450 million years ago down to 300 was due to the rise of land plants. Prior to about 460, 70 million years ago, there weren't any land plants. Land plants arose, and one of the things that they began to develop was lignin. They needed this lignin to keep their stems upright and to grow large and tall. And lignin is very resistant to biochemical degradation. So it tends to accumulate in the sediments. And so that accumulation gradually led to a fall in carbon dioxide in the atmosphere, and the accumulation of all of these tree-type remains helped to give us the Carboniferous coals in this low carbon dioxide period down here. Now, I want to give you one example that could be considered an analog today. That's here. This is 55 million years ago. We had a period when, from 56 million years ago, high carbonate sediments suddenly dropping out, the carbonate disappears, and then it comes back again after about 100,000 years. When we look at the carbon isotopes, we see they too changed at the same time. That tells us there was a massive injection of carbon into the atmosphere, probably 1,000 or more gigatons. When you put carbon into the atmosphere, the temperature goes up. So we see the temperature going up by 5 to 6 degrees and again falling back here. And when you put carbon into the atmosphere, carbon dioxide, it also goes into the ocean and it makes the ocean more acid. And so here we see the ocean becoming acid. That explains this dissolution. And we can see that in this deep sea drilling core. There's high carbonate at the bottom. Suddenly the carbonate disappears, you're left with red clay, and then gradually the carbonate comes back in. So we have ocean acidification. And sea level rose by about 12 meters. Now we have put 300 gigatons of carbon into the atmosphere at the moment. Are we heading along the same trajectory? Answers on a postcard. I want to get to conclude by talking about the sun. The sun's energy is obviously very important. Now you all know about the sunspot cycle. When there are sunspots, you may also know that when the sunspots are strong, the solar wind is strong. That's this ejected plasma, and it comes towards the Earth and it's deflected by our magnetic field. Now the solar wind is actually rather important because it deflects cosmic rays. When cosmic rays try to come down into the Earth's atmosphere from elsewhere in the universe, they are stopped or deflected by the solar wind. So if the solar wind is weak, then those cosmic rays can zap into nitrogen and convert it to carbon-14 and beryllium-10 isotopes. And that's good for geology because those get captured by ice cores and tree rings, and they can tell us how sunspot activity varied in the past. So let's just briefly look at the sunspot cycle. This is the latest data on the 11-year sunspot cycle, back through time right up to the present. And you see in the 1780s and the mid-1800s and this period here, we've had about the same number of sunspots at peak times. There's nothing particularly unusual about the modern condition compared with these two conditions here. What you can also see is that the sunspots are now in decline. So we're getting less solar energy. We can't call on a lowering of solar energy to explain an increase of temperature. How can we take that sunspot information back through time? We use these isotopes. So this is when you have a sunspot minimum, you have a cosmic ray maximum, you've got strong signals of beryllium and carbon-14. They tell us the conditions were cold, and vice versa for a sunspot maximum. So here we've got the cosmic intensity. All the highs represent lots of cosmic rays and cold periods, and at the other end we have many sunspots and a warm period. That's a medieval warm period. These are the peaks of the Little Ice Age, but it wasn't always cold. There were warm peaks here, and today in the 1950s we're about as warm as the medieval warm period. This is the natural envelope of solar change. Now, recently, a group has been working on bringing together all the ice cores, the stalagmites and stalactite records, the coral records, the tree ring records, to try and compile a record of past temperature change over the past 2,000 years. So here in black is their temperature record, zigzagging around a bit, okay? Now, how do we explain this pattern? We have to go back to the orbital data up here first, and the green line shows you the decline in orbital insolation at 65 degrees north, and here is the same. This blue line is the increase in insolation at 65 degrees south. But if you subtract the southern hemisphere one from the northern hemisphere one, you are still left with globally declining insolation. So our climate should have been cooling throughout this period. And so it is. When you look at the actual climate signal, it's been cooling more or less along the green line, which represents that northern hemisphere decline. The wiggles, ups and downs on this curve, are due to the sunspot changes that we just looked at. So you have to combine, by combining the sunspot data with the orbital data, you begin to see what the climate is doing, and you better understand the climate change. Now, what we see from this graph is that the temperatures, global temperatures measured by this group in past fossil materials, have increased significantly in recent years, especially after 1970. And we are now seeing plants emerging from under the Baffin Island ice that last saw daylight 4,000 years ago. So there really is something significant going on. What's CO2 doing? back to the ice cores, and here we're looking at the carbon dioxide levels from 260 to 400 parts per million in the ice cores, and they're all averaging about 280 parts per million for the past 1,000 years. Only in about 1769 did those values start to increase, and they increased exponentially until they mapped onto today's measurements in blue from the atmosphere. And it's all his fault. This is James Watt. And that's when he patented his steam engine, and everybody wanted one, you know, for pumping water out of mines, for running spinning jennies in factories. Factories began to grow apace, and the Industrial Revolution was underway. And so this is about the only thing that we can latch onto that would help us to explain what's happening in temperature since that period. Right now, carbon dioxide in the atmosphere is changing by about 20 parts per million in a decade. In the glacial period, it changed 20 parts per million. In 1,000 years, we are changing carbon dioxide in the atmosphere 100 times faster than nature did. So it's a pretty significant change, which is why these intergovernmental panel people are confident that we are changing the character of the atmosphere and leading to climate change. Now, my almost last slide combines, this is the insolation curve for the northern hemisphere. So there's the last glacial maximum on the right. Insolation increases. This warmth melts the northern hemisphere ice sheets, but then it declines. And it declines into what we call the neoglacial period, characterized by the Little Ice Age. Glaciers advance. This is what carbon dioxide is doing. Over the past 800,000 years, it's been oscillating between these two green lines, but over the past 10,000 years, you see almost no change. So it has not been a significant player in climate change through most of this 10,000 year period. It is now. That's carbon dioxide now, way outside the natural envelope. So our climate is a product of these many things added together, particularly the effect of the cooling into the Little Ice Age, which has now been modified by this massive injection of carbon. Our climate really should be down here. We should all be shivering in the Little Ice Age and having frost fairs on the River Thames. So now to conclude then, we've seen the great cooling, and we see that that was a change in the balance between the volcanic sources and these chemical weathering sinks driven by plate tectonics. And when the CO2 increased, the planet warmed and sea level went up. Then we've seen that there was, what am I trying to say here? Yeah, number two, that's right, there was no, the point I'm trying to make here is that there was no external source of heat to drive these changes in carbon dioxide. We did see a change in external heat when we got to these orbital changes, which proceed at a much faster rate, 100,000 years, 40,000 years, and so on. And we see that those did provide a source of heat that forced changes in carbon dioxide, and they fed back into the temperature rise. And so temperature and carbon dioxide and sea level all changed together within that natural envelope we saw in the ice cores. And then we've seen that the solar output also changed within the natural envelope, but the solar changes are relatively small. We've seen the carbon dioxide is well above the natural envelope of change. It's up at 400 parts per million. And we've seen that temperature is now above the natural orbital and solar envelope of the past 2,000 years, and sea level is still going up. So to conclude then, the geological history suggests that further rises in carbon dioxide will warm the climate more and raise sea level. That's what we concluded in 2010, and there's been no reason to change our minds since. However, these changes will be slow. And that's where I'd like to conclude. Any questions?
We have actually run out of time. So if you've got to catch some trains or something like that, please don't be ashamed or abashed about getting up and leaving. But I will take one question from each block. Could you also wait, if I pick you to ask a question, could you wait for the microphone to arrive? Of course, it's not for the benefit of the audience, it's for the benefit of millions of people who are watching this streaming on the internet. So why don't we just wait for the viewers to... Okay.
What was then the causes of the ice ages? Because there was one about 10,000 years ago.
What was the cause of the ice age? The basic cause of the ice age was that we ran out of carbon dioxide and the climate cooled. That's the tail end of the cooling of the past 50 million years is what we've been living in lately, which is the ice age. And we're still in it, yeah.
From what I understand, the Earth, the interior of the Earth is changing all the time. I think the solid core is enlarged, and Antarctica, in Antarctica, the glaciers, I understand, are melting from heat from within, not from without, and causing melting, which producing a slip plain, which then goes into the ocean, which then adds to the increased sea level. Can you comment on that?
Yes, the problem in Antarctica is that the ocean is warming and the warmth is getting in underneath the ice shelves and melting them from below. And so that thins the ice shelves and breaks off, causes more icebergs to break off. And as you thin the ice shelves, what that does, it removes the buttress that stops the glaciers running faster into the sea. So the glaciers are now running faster into the sea. So we've got more discharge of ice into the ocean. So the sea level is going up partly because of that.
Yeah. And
It doesn't have anything to do with the core of the Earth.
well, that was disputed a couple of weeks ago in some research, but I bow to your greater knowledge.
Okay, the National Oceanography Center in Southampton has measured the temperatures of the water under the Antarctic ice to show that this is actually happening, and they found no indication whatsoever that there is any heat coming up from the interior of the Earth. It's ocean heat being distributed under the ice. Okay. You should ask a lady.
I've not seen the little ice ages back in fashion. If you know, could you tell me why the IPCC report of several years ago dismissed completely the little ice age and used a meta-analysis to completely eradicate it? Could you tell me why the IPCC did that and still claims to be scientific?
Yeah, I can partly explain that. In the 1990 IPCC report, they used a graph of Hubert Lamb's. Hubert Lamb was a meteorologist at the University of East Anglia. And Lamb had been studying the Central England temperature record. And he found this very nice medieval warming and this little ice age. And they took that graph and put it in the IPCC report and mislabeled it global, which it never was. It was England.
With a meta-analysis involving times and all sorts of things he brought together, it made his name. He made, he became lead author and everything. I forget his name.
Michael Mann.
That's it. How did that take over?
Well,
Report.
what?
It was there just to get rid of the little ice age, and you have the little ice age there writ large, which I agree.
The latest data is on this graph here, which shows that there has indeed been this significant decline in temperature followed by a rise. And this part of the coldest part of the curve is Little Ice Age, and this slightly warmer part of the curve is the medieval warm period. Yeah, so that's the latest data.
Yeah, but they had a whole report where the previous report, the Little Ice Age, was there for a whole report for political reasons, presumably. The Little Ice Age gets written out of history.
Well, not anymore. Are you going to ask the lady a question?
In the interest of diversity, I must now ask a lady a question. There's a lady in the back there.
Yep.
This is not tokenism. One more question.
Actually, it is tokenism. I always try to ask a question for half the population. You have presented both the oxygen isotope curves and the marine isotope curves, and I'm wondering whether most scientists equate these as fairly equivalent and the stages are compatible.
Equivalent to what?
each other. So they're both showing essentially the same thing for the same time periods.
Yes, they are showing the same thing for the same time periods. Yeah, well, I mean, the reason I put up the leaf data from Antarctica was to demonstrate that there are several different ways of measuring the cooling through time. You can use fossil leaves, you can use stalagmites, you can use oxygen isotopes in deep sea cores, you can use ice cores, you get the same answer. They reinforce one another.